How does it feel to switch careers and start a postdoc at age 47? How was it to be one of the people who created the probabilistic programming language STAN? What should the Bayesian community focus on in the coming years? These are just a few of the many questions I had for my illustrious guest in this episode, Bob Carpenter. Bob is, of course, a STAN developer and comes from a math background with an emphasis on logic and computer science theory. He then did his PhD in cognitive and computer sciences at the University of Edinburgh, and he moved from a professor position at Carnegie Mellon to industry research at Bell Labs to working with Andrew Gelman and Matt Hoffman at Columbia University. Since 2020, he's been working at Flatiron Institute, a nonprofit focused on algorithms and software for science. In his free time, Bob loves to cook, see live music, and play, of course, role-playing games. Think Monster of the Week, Blades in Dark, and Face. This is Learning Bayesian Statistics, episode 76, recorded January 9, 2023. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the podcast, learnbayestats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merge, everything is in there. That's learnbayestats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayestats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men, dropping placebo-controlled science like I'm Richard Feynman?
Bob Carpenter, welcome to Learning Bayesian Statistics.
Thank you.
Yeah, thanks a lot for taking the time. I'm really super happy to have you on the show, because I've been meaning to invite you for a long time, and so I'm super glad that you could find some time out of your busy schedule to come and talk to the listeners, who I can tell you are very excited to hear about you.
Okay.
Let me start then. And as usual, I always like starting by the background of my guest, because, there are so many diverse and inspiring backgrounds that I find that fascinating. So let's do that with you as usual. So let me ask you, well, how did you come to the stats and data world? And was it more of a sinuous or a straight path?
Well, I don't know. I started doing a lot of probability when I was a kid because I played a lot of games, especially role-playing games. And my dad was a bookie who used to have me calculate the odds for bets. So I started doing probability very early on, but then when I went to undergrad, I really wanted to do logic-based AI and natural language semantics, and did that for many, many, many years. And only when natural language processing started to make a turn into statistics did I take this up seriously, sort of in the mid-90s. We had just hired Chris Manning at Carnegie Mellon. He was teaching an intro NLP class in stats, and that's what got me hooked.
I see. Okay, so actually it started very early, your statistical practice.
Yeah, although, the way statistics was done in natural language processing in the 1990s was not particularly sophisticated. So it took, I felt like I really needed to leave my job working in industry in natural language processing and go hang out with Andrew Gelman for a few years to actually learn statistics. I found it very hard to understand just reading textbooks.
Yeah.
So I could learn the basics. I could learn how to code bugs. It was actually understanding the subtleties. There's a lot there.
Yeah, I definitely relate to that. It's like reading the textbook is a good first step, but then when you start practicing, it just makes a huge difference in the practical way that you can use it and really understand it. To me, it's really when I started making kind of like classic errors and mistakes that I really started to understand what all this was about. And so I'm actually already very curious about a lot of things, especially on the NLP that you mentioned, but let me not get off course right now and come back to that a bit later. But so to continue on your basically painting a picture for the listeners about who you are, where you come from and what you're doing, can you tell us how you would define the work that you're doing nowadays, actually, and what are the topics that you are particularly interested in?
Well, I'd say pretty much my whole career I've been doing the same sort of thing, which is building programming languages and APIs for people to use to do whatever they're doing, because I like kind of working at that meta level of a language. So, it's what led me to develop Stan in the first place, the language side of it. Nowadays, though, now that I've moved, a couple of years ago, I moved to 3 years ago now, I moved to Flatiron Institute from Columbia University. And that's cleared up a lot of my time, which used to go into fundraising and managing a group of postdocs and things, where I can do a lot more work on my own now. And I'd say nowadays I'm working much more on algorithms. So we're working on variational inference algorithms. We're working on the geometry of transforms for constrained variables. So I'm doing much more higher level stuff than just low-level Stan coding. So my day-to-day looks less engineering-oriented and more research science-oriented, I would say, is the biggest difference. Having said that, though, I still spend half my time developing code. So we're really excited about a bunch of packages Brian Ward and I are rolling out with Edward Raldis that are sort of exposing Stan through different languages like Python and Julia. And then we're building algorithms on top of that. So I'd say that's sort of what's keeping me busy day to day now.
That sounds very cool. Do you want to talk a bit about that?
Sure. I mean, we have, it's been a struggle with the interfaces in Stan because we have a language that's independent of any existing programming language that we build from scratch, which means people have to wrap it in languages that they're using. And the original versions of RStan and PyStan that we designed were communicating in memory to the Stan C++ code in the back end. The way we did that, though, was through high-level interfaces like RCPP and Cython and R and Python, which imposed a lot of C++ binary compatibility. And recently, when Ed Raldis was visiting Flatiron last summer, he's one of the Stan developers who's a professor at Cal State Chico, he wanted to develop algorithms in Julia, and we didn't have any way to expose Stan models in Julia. So he started working on low-level in-memory access, just a very low-level C interface, foreign function interface to Julia. And while he was at it, we were like, can you do the same thing in Python and R? And he figured out like the low-level interfaces to both those. There's something called the .c interface to R and the C-types interface to Python. The nice part about those is that they only require memory compatibility. They don't require the whole compiler chain, right? Which was a huge pain for RStan and PyStan installation. CRAN as well on R is a very difficult thing to deal with because they insist on packages being very small and they don't have a dependency management system for packages. So we're about 2 years out of date on RStan because of CRAN. And I don't know that we'll ever get another CRAN version up again of Stan because they changed policies. So that RStan was the only way to really get a Stan model. So a Stan model is a C++ encapsulation of data, basically goes into the constructor, and then it defines a log density function, which is automatically differentiable. We wanted to be able to access the derivatives, the gradients, the Hessians, and the variable transforms, because Stan automatically transforms variables from constrained spaces to unconstrained spaces and back. So Bridge Stan basically is just an interface that exposes the Stan C++ model into those languages in an efficient way that doesn't involve any copying in memory. And now on top of that, we're building inference systems starting in Python to just implement all the standard algorithms, because there turns out to not be good reference implementations of any of the MC stuff in Python. It's all like in Stan tied up, or in PyMC or something. It's all tied up with a particular probabilistic programming language. So there's a lot of good implementations of it, but none that make it particularly easy to just wrap your own gradient and log density function and go. So So we're combining these two things of bridge stand, which will expose those gradients, and then just building reference sampling and posterior analysis tools and things, which will be hopefully useful both pedagogically and for us to be doing research in for building things, because you don't really want to be developing algorithms in C++. It's not a good experimental prototyping language, at least for mortal programmers like me.
Yeah, like me too. And have you looked into blackjacks? That's in Python.
We have. That's one of the things where we tried to get our algorithms working in blackjacks. We tried to get just our log density gradient function, but it makes a lot of assumptions that you're going to actually be using jacks.
Yeah.
Underlyingly. So we couldn't actually get it to work without it trying to auto-diff our code with jacks. Maybe there's some way to do that, but we couldn't figure out how to do that.
I see. Okay.
Now, the other way around, we've gotten the jacks models working with our system. That we can do.
I see. Okay. Damn, already super cool stuff. Like, let me backpedal a bit and ask you another traditional question, which is, do you remember how you first got introduced to Bayesian methods, actually, and how frequently do you use them nowadays?
I would say it's kind of a subtle introduction, because I started in natural language processing and speech recognition. And, like a lot of places, people are like implicitly Bayesian without actually sort of understanding that they're taking a Bayesian interpretation of things. So I think most of the NLP stuff kind of has a Bayesian perspective in it. Like it tends not to do Bayesian inference, but it tends to fit Bayesian models. Right. So which I think is true of a lot of machine learning, where they talk about the models in a Bayesian way. You talk about speech recognition as like a noisy channel decoding model, where you build an acoustic model, right, based on what people say, and then you build a language model of what they're going to say, and then you just do the standard like Bayesian inversion, right, to actually decode what they're saying. So I got exposed to that very early, but getting exposed to really taking uncertainty seriously, to building hierarchical models, to like pushing your uncertainty through inference, to do like posterior predictive inference, that all came much later, after I started learning bugs and JAGs. Maybe it would have been about 2005. I was working at a small NLP company, and we were dealing with a lot of crowdsourcing problems. Every time we got a new customer, they would be like, hey, can you guys recognize rap artists and songs in text? And we'd be like, sure, we just need a training corpus. Now, me and my partner, Breck Baldwin, would go back and start annotating a lot of data and try to do our best with that. But we wound up with lots of data annotation problems. We like worked with epidemiologists who were annotating like chief complaints in emergency rooms. And we were constantly faced with these crowdsourcing problems. And it seemed like a natural sort of place to apply Bayesian methods. So I had known Andrew Gelman personally for many years before I started working with him. So I asked him if I could start hanging out in his research group. So I'm working at my company. I'm hanging out with Andrew and Jennifer Hill in their multiple imputation group. And I'm like stealing some of their time on the side, so they could help me build one of these models. We wound up building a crowdsourcing model, which wound up to be absolutely isomorphic to David and Skeen's model. So Phil David built a model in 1979, right, which is a really cool crowdsourcing model. People are using it all over the machine learning world now. And many people like me rediscovered it. Well, really, this was like Andrew and Jennifer rediscovered it by me telling them what my problem was. So I think like a lot of things, having that one particular instance, it was kind of a complicated, discrete model problem, but having that one problem that I actually cared about. I really cared about the answer. It wasn't a textbook problem. I wanted to like put this into practice. That made me come to grips with hierarchical priors, with all the computation, with all the inference that you were doing. And it just changed my entire perspective on how to do calculations. And after about a year of working with Andrew and Jennifer sort of on these problems and applying them to crowdsourcing, I wrote dozens of blog posts. I wasn't really writing papers at the time. I finally decided, both I and my partner in my company were kind of bored building, like we were a 2-person natural language company. So we could build classifiers, we could build spell checkers, but we couldn't build anything large scale. And we were just getting bored building another, Twitter classifier. Like, sure, it may be in Korean this time instead of in French, but, sure, it's the same technology. So I'm like, okay, I'm going to quit. Go start another postdoc. I basically said, Andrew, can you hire me for whatever you can pay me? And he's like, well, I got a couple of postdoc openings. Maybe I could hire you that way. So I was at a very late stage in my career, went and jumped on into a learning situation, which was a lot of fun. I don't think I could have ever learned this on my own while working a full-time job. Even though I was spending all my spare time doing it, I just don't think I could have, without a mentor really helping me, I don't think I could have crossed the gap.
Yeah, that's definitely hard. But I love that story because you were 47, right? When you started a postdoc in a new field. That's super inspiring, though.
Well, all of my peers were very jealous. Like my peers who were deans and department heads, they were like, you're going to actually get to go do work and learn stuff again. He's like, all I do is management. So
nice.
So it's nice. I would highly recommend it.
Yeah, I'm curious, how did it feel when you did that?
Oh, I mean, it felt just like doing research. Like research always feels the same. Once you've gotten to a grad student or postdoc level, everyone kind of works together. It's not it wasn't like everybody treated me like a kid again, right? Going back. So it was really it was a great learning environment because for a couple of years, I didn't have any responsibility. When we were first building the first version of Stan, I had no responsibilities for teaching, for supervising, for fundraising. There's just a couple of years of funding I had, didn't have to worry about anything, which is a great way to get work done and learn things. So it felt like going back to grad school really more than going back and doing a postdoc, except I didn't have classes. I mean, I'd sit in on Andrew's classes.
Which sounds like fun. I mean, Andrew has been on the podcast a couple of times, and definitely I was absorbed by the conversation. I'd really love to attend one of his lectures for a semester for sure.
Yeah, his classes are great master classes. If you know the material and want to discuss them, because Andrew's kind of bored at teaching the intro material. So if you go to one of his classes, it's almost always a discussion of the high level stuff. It kind of reminds me of David Mackay's book on information theory, which is a great intro to neural nets, Bayesian inference, machine learning, but it's very particular. It's very a couple page chapters that really give you insight into something rather than just regurgitating the formulas that everybody knows. And I think Andrew's classes are very much like that. You go away, you always learn something going in one of Andrew's classes. You learn some subtlety that's not in the textbook.
Yeah, for sure. If people don't know Andrew's style, I would recommend listening back to the episodes he was here for. So if I remember correctly, it was episode 20 with Aki Vetari and Jennifer Hill for their book, Regression and Other Stories. And I think episode 47, I have to check, but he was there with Merlin Keidemans talking about the model they did for the US 2020 election.
Oh, yeah.
So I put that in the show notes for people who want to listen to that again. And also we should put the book you just told us about. So it's by David Mackay and it's called Information Theory, right?
Yeah, it's a long title. It's got 5 nouns in the title or something, but information theory is one of them.
Okay. Yeah, I think it's Information Theory, Inference, and Learning Algorithm.
There you go.
Yeah. So I'll put that into the show notes.
It's characterized by describing logistic regression as classification with one neuron, because it takes this neural network approach to everything. And so it's quirky, but it's very insightful. Basically, we coded HMC based on their discussion, based on Mackay's discussion. Right? There's a really nice discussion of Hamiltonian Monte Carlo in there.
Interesting. Well, it is in the show notes, people. So if you want to check that out. Awesome. And well, you already touched a bit on it, but you're one of the co-founders of Stan. So I'm guessing that's when you started all that postdoc stuff and so on. So yeah, can you tell us a bit about the origins of Stan and how and why you got involved? And if people want more details, I put in the show notes talk that you did about 10 years of Stan and how it is to nurture an open source software community. So it's a YouTube video. I put that in the show notes already. But yeah, maybe tell us something here about the beginnings of Stan and maybe something that's not in your talk on YouTube.
Yeah, I can't remember exactly what the talk was, but so I apologized if I duplicate myself. But the project really started because Andrew wanted to fit better hierarchical models. He took his and Jennifer's book before they rewrote it with Aki, had a bunch of models in it, and he used a lot of LME4. It's a max marginal likelihood package in R that's super popular. And it turns out that modeling language for LME4 was not quite rich enough to express all the models in Gelman and Hill's book, or now with Aki, the new one. And he hired me and Matt because basically Andrew got money that sort of fell on him out of the sky. Some people had some grants, were leaving Columbia, gave the grants to Andrew. So he just took a flyer on hiring a couple of computer scientists. So he hired me and Matt Hoffman, who just finished his PhD with Dave Bly. And he wanted us, we spent the first months while trying to get our terminology together, right? So we could all talk to each other, which was challenging. Because Matt and I were both coming out of machine learning, and Andrew's very, very particular about language and everything else. He's fantastic that way. So it was a big learning curve in the beginning just so we could talk to each other. But then what we were trying to do is Matt and I were trying to design a language that was like an extension of LME4 that would cover all of Andrew's books. And eventually we just went on and we couldn't figure out how to do it. And then finally I said, why don't we just build something like bugs? I think we can, at that point we'd gotten the advice to do Hamiltonian Monte Carlo, to do automatic differentiation. And I'm like, I can see how, because my own background, I should say, is in programming languages and natural language processing. So I went to Edinburgh for a PhD, which has a great programming languages group. And I spent a lot of time hanging out with those people in programming language design. And my early academic career, I spent a lot, I wrote a book on programming language theory, back when I was doing logic programming. So it doesn't look anything at all like Stan. So I'd had a strong background in designing languages and compilers and things. And I thought, well, really all we need to do for HMC is have a system like bugs that will let us evaluate, that will compute the log density function in a way we can auto-diff it. So I just sat down with bugs and said, what do the statements in bugs look like if they're going to just, instead of doing sampling and defining a graphical model, which is what bugs or JAGs does, instead, if we took those from a more procedural programming language and thought of them as just defining a log density function, what would the contribution of each little piece did? Once I made sense of that, it was pretty easy to sit down and write a prototype for the Stan language that was very much like bugs, but my own background is in type theory. So I spent a lot of time both in natural language semantics and in programming languages working on simple type systems. So I wanted to build something that didn't look like R or Python or JAGs or bugs, and instead was strongly statically typed like C or Java or a language like OCaml or Haskell or something. So that's what I thought was going to be the main bottleneck for people. I thought people were really not going to like the typing. And there's certainly people have a bit of difficulty with arrays versus vectors and things in Stan, right? We use vector types for all of our linear algebra and arrays for everything else, which still confuses people. But overall, that was not the kind of bottleneck I thought it was. But the thing was, at the same time, we were pulling the lid off of JAGs. Like JAGs has a very clean code base. It's a very inefficient code. It's amazing for somebody who's not a computer scientist who wrote it by himself. Like the fact that Martin Plummer got this done and it's as cool as it is just amazing. But it's written with a bunch of R infrastructure, right? It's using R code, using R classes, R definitions, and R itself is super inefficient the way it's coded. So as a result, JAGs inherits a lot of the clunkiness from R. So we were thinking we would just rebuild that. We're like, okay, we'll just build a better Gibbs sampler because we'll just do the software engineering. And Matt started writing vectorized versions of things in JAGs, and we started, because I still hadn't learned C++ at this point, right? So Matt was doing the actual coding at this point, and I'm like, if we're going to do something like this, I better start learning C and C++. I mean, I had known C, but I hadn't known C++, so that was a huge effort as well. But Matt started optimizing JAGs code. But then we realized that we didn't really just want to make a faster Gibbs sampler. It's like Gibbs sampling, no matter how fast it went, is still not going to go fast enough in dimension. It still scales very poorly. All the state-of-the-art methods are gradient-based. So we knew we kind of needed to jump up from Gibbs sampling. So after a few months of trying to develop a new language that looked like LME4, trying to make JAGs go faster, we're just like, okay, we need to start from scratch. We'll write our own language. This was before we had constrained parameters or anything like that. There were just the three main data parameters model block. But it was actually quite fast building the prototype. The hardest part was just learning C++. All right, so Daniel Lee and I were the ones who built most of the first version code. Matt built the sampler. He helped with the memory. design for everything, because Matt is like a crack C++ programmer, but he doesn't want to spend his time doing that. So he was like the C++ advisor for us on the project, but Daniel and Lee and I did most of the coding. But that's how it started. It was like, can you make hierarchical models go faster in a way like LME4? And we were like, yeah, not really, but we can build a faster version of something like bugs or JAGs, right, that will actually solve some of these problems for you. Although, ironically, it turns out hierarchical models are still some of the hardest models to fit. If you just take like Radford Neal's funnel example, which is a hierarchical prior with a normal prior with no data, right, that's still something you can't fit with HMC. There's no fixed step size that'll deal with the bad conditioning of that distribution. Nuts doesn't help, right? So it's still something that you can't solve. So one of the things I've been doing recently is try to figure out how to build samplers that will sample those problems, right? I think what we did with Stan was we just pushed this back on the user. We're like, no, it's not going to sample the model the way it's written. You have to reparameterize the model. Right? It's your job as a user to give me a parameterization where the posterior looks close to standard normal. Then we're good to go.
Yeah. And that definitely still is a bottleneck for sure. I mean, especially for beginners, I can see that. And I mean, it's the same in PyMC, as you're saying. It's like, ideally, we would like the computer and the algorithm to do that by themselves, but they still can't. So we have to push that on the user's side, which makes things a bit even more trickier to adapt and adopt for beginners.
Yeah, and it gets into issues like trying to it's even worse in multivariate problems. So doing like Neal's funnel is relatively easy to build the non-centered parameterization, but when you have something multivariate for that, it gets much harder. Now all of a sudden it's Cholesky factors and everything else floating around. It's just a lot. The code gets a lot clunkier. Right. This was one of the things that led Maria Goranova to build SlickStan for her master's thesis. It was there's no way, like the worst part of Stan, in my opinion, is that there's no way to encapsulate modules. There's no way to write like a hierarchical prior in Stan. Right. This was the largely the focus of like my prob talk based on this year, which was based on what Maria was doing, kind of surveying a bunch of the systems. In the end, I decided I really like Turing.jl for a language and for, the expressiveness. It's like bugs, only better.
Interesting. So for listeners, by the way, Maria Goranova was in the podcast, episode 17, where she talked exactly about the project that Bob was mentioning. So definitely check that out if you want a more detailed review. And that's exactly about that. Like, how do you parameterize your models automatically? And the whole project about that. And that was, super cool episode. I really loved it.
Yeah, she did a cool internship with Matt too, where she did discrete parameters. Like, I don't know if she was talking about that then, but she's done a bunch of cool work.
Yeah, definitely.
I keep meaning to follow up with her. I haven't actually contacted her to see what happens after the Twitter blowout. So since she moved to Twitter.
True.
She may be back on the job market.
Yeah, that's true. And actually, I also have a few episodes about Turing. I put two in the show notes, episode 19 and 36, about developing Turing.jl and the Julia ecosystem with Cameron Pfeiffer and Martin Trapp, who both are core developers of Turing. So definitely take that for a walk.
Yeah, I'm very jealous of how clean Zygote is for their autodiff. We just did like complex derivatives and fast Fourier transforms and stuff, and I was almost just crying looking at the 3 lines of code it took to write that in Zygote and the 100 lines of code it took to write it in C++ and Stan. So. Yeah.
Well, I mean, you started that way earlier, and you were also one of the motherships of the probabilistic programming languages. So, I mean, definitely all the PPLs out there owe something big to Stan. So, I think I'm speaking in the name of everybody when I thank you, Bob, and all the team for your hard work and on getting the first version of Stan out to the world. And I think that was definitely trailblazing work. So yeah, definitely thank you for that.
Oh, you're welcome. It's certainly been fun.
Yeah.
And it's not me, obviously. It's a big team of people, as you will see if you go and look.
Yeah, for sure. Like all open source endeavors.
Yeah, by the time we had the first version released, I think we had 6 or 7 developers by release day. Like Ben Goodrich was really critical for getting all of our multivariate stuff. I still remember the first implementation I did. Like I was so ignorant that I literally wrote multivariate normal. I wrote our first multivariate normal implementation as just y minus mu transpose times inverse sigma times y minus mu. And I'm like, what's wrong with that? And people are like, no, Bob, you do not take inverses in linear algebra. Where did you go to school, you idiot? So I had to learn a lot about computational linear algebra, other stuff like that as I went along too. But that I would never have been able to do by myself, right? It was like we had both Michael Betancourt and Ben Goodrich and Andrew, all of whom were bringing in like heavy duty stats background into this.
Yeah. I mean, that's the beauty and magic of these open source projects, right? It's just like so much work and people working behind the scenes, but also I really love that spirit of open garage, and like nobody is pretending to know more than they do. And like you can openly make mistakes and it's going to be fine. People are not going to scold you for that. On the contrary, you're going to learn a lot. And it's definitely one of the safest spaces I've encountered to work and learn.
Yeah, we've tried to be very, very open. Now, having said that, I kind of got kicked off our mailing list for being too rude to people. So I'm back on our mailing list again, but it's a very delicate operation talking to users. It's like you try to be nice, but it's very challenging. It's very challenging to be nice. It's very challenging to have the users believe you're being nice.
Yeah. Oh, yeah. Yeah, definitely. I understand that. Especially since the open source way of, giving feedback and being like open and transparent can be very different from a lot of companies, private companies. And so if people come with that mindset and they see they clash with the open source mindset, it can be really a really different world for them. And it can seem very violent, even though it's not at all. But yeah, that's definitely something that I also have to keep in mind each time I need to talk to users.
Yeah, because people are very invested in their ideas. They're very, they're often very stressed out because they've spent days trying to get your system installed or working. They have deadlines coming up. So yeah, it's a lot of pressure in different ways.
Yeah.
But overall, our users are great in understanding. And I find if you just tell them, look, the reason this is broken is because we don't have a developer for this, like, you're welcome to come help us fix it. Otherwise, we'll get to it when we can get to it. People will be understanding rather than trying to be defensive and say, look, it's okay as it is. Like we've just owned up to all of our mistakes. I was very happy to see that, what's the name of this package? Nimble did exactly the same thing. So they broke their inference, right? And then they did a big campaign of publishing that they broke their inference and that people needed to, and they fixed it, that people needed to upgrade. We went through that in one of our releases. We had an off by one error in HMC, and one of our users found it with 1 million iterations on like the third decimal place or the second decimal place of a correlation in a multivariate normal. Our unit tests that ran 10,000 iterations didn't pick this up, but some user ran it 1 million iterations and said, you're off by like 1% on the correlation parameter and you shouldn't be. We're like, no, we shouldn't be. And we realized that we'd introduced an off by one error when we were moving from the slice sampling version of HMC to the multinomial version of HMC. But I went on Andrew's blog. I top posted stuff on our forums just saying, sorry, everyone, this is our fault. We blew it. Like, please fix as soon as you can. Right? And I find if you're open like that, people are much more understanding than if we had tried to sweep it under the rugs. Like I won't mention packages by name, but I've seen one of these packages release a release saying, well, we've had a bug for a year that we didn't tell anybody about, and we just fixed it now. And you're like, that's not a way to earn trust with your users.
Yeah, for sure. So yeah, that's definitely an interesting story, and that definitely relates to what I was saying about the open source culture. So that's actually great. Thanks for contributing that. And actually, you were saying that it was super fun to work on Stan, and well, I'm guessing you're still involved, of course. And so, but I can imagine that there were a lot of difficulties. And so I'm always interested in that. Can you tell us which difficulties you encountered with this project and what you learned from them?
There were a lot of difficulties with this project. One, I learned C++ is about as bad as it looked like from the outside. Like, it's super great that you can control memory, but just the fact that there's so much undefined behavior in the compiler spec just is a disaster for consistency. So I learned a lot about C++, a lot about continuous integration and all of this stuff. But I think the thing that I learned the most was that these projects are about people. It's not about the ideas. It's really about managing people. And it's really like the biggest trouble we've had is when we moved from like 2 or 3 people sitting in an office where we pretty much had divided the project up and everybody was doing their thing, to where we had to coordinate a bunch of stuff and we had different ideas about how to move from version 1 to version 2 of Stan, and we could not agree. We spent about a year sort of deadlocked before we sort of came in and got governance as part of the project. So we started, during that point, we went from, so the project feels very different at different scales. It feels like one way when there's 2 or 3 people sitting in an office. It was just Daniel, me, and Matt. We were sitting in an office, right? And we could just talk to each other. It was like, that felt one way. Now we've got 40 developers spread all over the world. It feels very, very different. Getting from there to here was really the hard part. And I think a lot of it was managing the community, managing both the community of the developers and managing the communities of users, right, to do this. And I think the big thing that we did, I think where we went wrong is Sean Taltz and I, at the point where we needed governance, we had both been in industry and we thought, industrial models work really well. It's very clear who has decision-making process. It's very fast. Somebody always makes decisions, right? They may not be the right decision, but you get stuff done. Right? I was talking to other friends of mine who were tech managers, and they're like, look, if you've been debating these options for a year and you can't decide, just do one. Obviously, they're too close to decide on theory. Trying to get a bunch of academics to just do something before they figure out which one's the best is challenging. Right? It's just not how we're brought up. We all like arguing about third-order details of things. That's what drives you into academia in the first place. So moving the project at that point, what we did is we moved to governance where we had a technical manager and then we had technical leads for each of our projects. Right? First, Sean was technical manager because I didn't want to do it, and then I became technical manager. Maybe we did it the other way around, but anyway, our developers did not like having somebody in charge, right? It sort of cuts against the grain of open source projects. It sort of, I think, undercuts the ownership that people feel in what they're doing. So that didn't work well, and I was probably more stressed than I've ever been in my work life at that point. When Stan was moving from version 1 to version 2, it really felt like the project might fall apart because we all couldn't decide where to go. Then we put me and Sean in charge. That also didn't work well. And then finally we moved to an Apache-style voting system where nobody's in charge, but if issues come up that people don't agree on, like a pull request, that some people say don't merge it and other people say merge it, then now we vote. But just having that mechanism there was huge. And I learned a lot about how people work on big projects. I'm still not a good manager. Right? I very much, when I made the move from academia to industry, I was really apprehensive about sort of giving my day-to-day control to a manager. But in fact, I loved it. My manager, John Nguyen, when I worked at Speechworks, was way better than I was at figuring out what I should be doing on a day-to-day basis. And he figured out what all 30 people on his team should be doing on a day-to-day basis, which meant we went really fast. Right? And if you think you're going to get that on an open source project, you're going to be very disappointed. Right? And Sean and I think we're coming in with that idea that, hey, we can make Stan like a real industrial project. We can really start flying on this with some decision making, but not so much. So I think dealing with the people has been the sort of hardest aspect of this. I mean, there's a lot of technical challenges, obviously. Working cross-platform is huge. If I could go back and undo the decision that we would support Windows, I think that would probably save most of the technical hassles of our project. We'd lose a lot of users, but I'm still surprised at the number of statisticians who use Windows day to day and don't want to use the Linux. They've got a Windows machine, but they will not open up the Linux subsystem. We're like, hey, everything's easy with the Linux subsystem, just works like that. And nope, that's a bridge too far.
Bob, I feel like you're saying out loud what a lot of open source developers are thinking.
Okay, well, Yeah.
Yeah.
I mean, Mac is bad too. Mac, like at one point, their Xcode distribution changed the template parameter depth and broke all of our programs.
Yeah.
It was a bug in their release, but it basically broke everybody's Stan program. Then we had to go like custom hack it, do a quick release to patch the bug that Apple introduced. And, so it's a lot of time dealing with that kind of stuff.
Yeah. I agree. I was surprised, and I keep being surprised also at the time we have to spend on the cross-platforms problem. And actually, it's something that also motivates the current work that we're doing on the PyMC side, where we're trying to ship the Numba backend, because that way we could rely on Numba for all the backend work, and we wouldn't have to deal with the cross-platforms problems, because they would be dealt with in a way better way by the Numba team, and we would just plug into that. And it's something that, in particular, Adrian Zabelt is working a lot on. I got him on the podcast for episode 74, and Adrian is absolutely brilliant and generous guy. So if you're curious about what he's doing, definitely listen to episode 74. We talked about NutPy, which is the re-implementation of nuts that he did in Rust, with actually really, really good results and speedups. We talked about that. We also talked about the zero-sum normal distribution that he came up with, and that's now in PyMC. So yeah, I mean, cross-platforms problems in general.
Yeah, I'm afraid I haven't been able to keep up with the PyMC platform stuff. I thought you were going to Jack's backend.
Yeah, I mean, there have been a lot of changes. But basically now we're on a more stable course where we have, again, our own backend, which is called PyTensor. And the goal is to basically use Numba with PyTensor so that the C backend custom from PyMC can go away, and we can use Numba for the backend, which should both simplify a lot the code base for PyMC, the installation for PyMC, and, as I was saying, the handling of the cross-platform problems. So actually, I'd like to talk to you a bit about that, about the hurdles, basically. And I'm curious, what do you think the biggest hurdles are currently in the Bayesian workflow? What do you see people being bothered by most of the time, mainly in the user base?
Yeah, I mean, we're putting a lot of effort into thinking about this. It's basically what Andrew's doing pretty much full time now. Andrew and Aki we wrote a long paper, like an 80 or 90 page sprawling paper. About 10 Stan developers contributed, threw paint at the wall, and we got a 90 page long paper. Now Andrew and Aki are trying to turn it into a book. And what we're realizing is so much of this stuff is not written down. So much of the stuff that you need to do, right? It's like it's not in the textbooks. So I think the thing that's really challenging, that's sort of been challenging all along, is still the two problems of being able to express your model, being able to write it down, being able to convert from the math that you have written down to the model, or in some cases, formulating the math that you need to write down. Because we have a lot of users I'm sure you get this in PyMC, we get a lot of users who are applied statisticians. They may be physicists or biologists or sports analysts of some kind. And they don't all have like PhD levels of statistics background, So a lot of those people need a lot of help formulating models. But often those people are good programmers, whereas the flip side is we get a lot of statisticians who are excellent at differential equations and stochastic differential equations. They know measure theory, but they don't know how to write a program with indexes, right? So actually having somebody sort of go from the conception of the model to the actual working code, me coming from computer science, I thought that was the trivial part, because that's always been the easy part for me, is the figuring out how to code it once I know what I want to do is always the easy part. That turns out to be a huge bottleneck for most people. And it's a huge bottleneck for me when what I want to do is explore a bunch of different models, right? So the problem with workflow isn't so much if I have a model, can I code it? It's that I don't know what model I want, that I've got some data, and I generally want to fit as big a model as I can with as many interactions and predictors as my data will support. But I don't really know where that is until I start playing around with the model. right? So there's a lot of back and forth there, and none of these systems provide really good tools for exploring multiple models. It's something I've been asking all the PyMC and Pyro and other developers is how much workflow support there is at the high level. In Stan, we have a problem in that there isn't a good way to formulate sort of chunks of models, right? Whereas in something like PyMC, you could easily formulate the code for a hierarchical prior, formulate the code for a couple different priors as Python programs and swap them out as part of like a Python workflow. But I don't really see people doing that a lot. And I see them doing the same kind of thing people did in Bugs and Jags, and they write 10 full PyMC models that are like, you write one, copy and paste, modify it a bit, write another one. Right? If there are examples of people sort of organizing the code into workflow for that, I'd really love to hear it. I generally ask any other PPL developer whenever I see them if they're doing that, because we want to figure out how to do that. You can't really do that easily in Stan at all, but we want to start thinking about how we can encapsulate pieces of the workflow that are smaller than a whole program, but bigger than just one line.
Yeah.
Then there's all the problem of once you've written your model down, have you got the right parameterization? Can you debug it? And can you actually sample from it? Right? The debugging tools for all of these things are not great compared to writing regular code. Trying to debug Stan code is like writing some print statements inside of it. It's terrible. Right? It's a little better for some of the embedded things, but I think it's still difficult to get into the middle of sampling and see what's like going wrong. Right? If gradients explode somewhere, trying to diagnose all that is, all of a sudden now you're into like geometry problems, sampling problems, convergence problems. You're into all these like computational stats things that you don't want to be in because all you want to do is fit your damn model. Right? You're like, I've got some data, I've got a model or a few models, I want to fit them, but that is still hard. I wondered why it wasn't so hard in the frequentist world, but I think that's just because they don't fit a lot of different models. Right? Everyone isn't trying to fit 100 different kinds of models to everything.
Yeah, that I don't know about, I have to say, because most of my experience in statistics is on the Bayesian side.
Me too. So take that with a grain of salt.
Yeah. What I can say, though, is that, yeah, you definitely can do those encapsulated bits of models with PyMC because, yeah, like you can encapsulate that in Python functions. So for sure, like we do that a lot at PyMC Labs, actually. Like most of the time, I mean, in the development phase, it's usually useful to do the copy-pasting stuff that you are talking about. But then once you have your models and so on, encapsulating Python functions is like the thing we do to deploy in production, basically. So for sure. And like hierarchical priors, for instance, I do that all the time, especially if you have like a non-centered hierarchical prior, for instance. Yeah, it's super useful.
I'd be really curious if you have code you can share for that, because I've been looking for examples of that pretty much for the last 10 years.
Oh, yeah. Okay. Yeah, I'll see what we can share. I know that I did that for a client, but I don't know who shareable the code is.
Right.
Yeah.
Yep.
Yeah, but I mean, it's not that complicated to come up with some sample data. Yeah, and definitely I find that super useful too because I'm terrible at, keeping multiple dimensions in my head. I'm like, it's awful. So it's like each time I'm working on a hierarchical model, my main problem is, wait, where I am in the pyramid now, and like, what's the shape of that thing? And so having the dimensions and coordinates that we have now in PyMC, instead of specifying the hard number shape, and also having those small functions where you can just say, okay, hierarchical prior on that, and then just sample prior predictive stuff like that. That's super useful to me. And then, like, also we use more and more Bambi, which is like BRMS for Python and PyMC. And that's definitely super useful. So not for all models. Some of them, you really want them in PyMC and completely customized. But for a lot of models, you can use Bambi and get a great model out of that, which encapsulates all those things and automates a lot of the decisions for you.
Right. We found that particularly useful in getting good priors and doing things like preconditioning the data matrix and stuff, which we show people how to do it in our user's guide. But, you want to write a linear regression, the textbook version is like 10 lines of code. right? The real version that preconditions, that postconditions, that does everything sort of efficiently, all of a sudden looks really complicated, right? Because you like transform the data, you transform the parameters, then you transform them back, right? So it's really a lot of work.
No, exactly. And I'm actually working on an online course right now and developing a lesson about categorical regression. And I'm actually showing how you would do that with PyMC and then how you would do that with Bambi. And then that shows you how much automated things Bambi is doing for you. Because, yeah, as you were saying, like transforming the data or not, setting the priors. If you're dealing with categorical data, well, you need a reference. I mean, you can use the zero-sum normal, which is what I do when I did those models with PyMC. But here, if you use Bambi, well, Bambi will choose the category for you and do all the pivoting stuff. And you have to take care also of the categorical predictors, which need a pivot too. So it's like if you do that in PyMC, it's a lot of code. And you have to go to the back end, use PyTensor. Here with Bambi, you just do the stuff, and Bambi will handle that for you. So that's super cool.
I think the future might be combining some of these systems. That is, combining the Bambi-like ideas into the PyMC code. But
yeah, definitely that's a world I'd like to live in. And talking about that, thanks for that great segue, because I wanted to ask you about the future of Bayesian stats. And basically, what does it look like to you? And more specifically, what would you like to see and not see?
I don't know. I'm not much of a precog future seer. Pretty much every guess I've ever made about the future has been wrong. So I'm reluctant to speculate.
I mean, you can see that as a wish list instead of a prediction.
In 2 years, ChatGPT is going to maybe be writing all of our code, right? I don't know. Maybe it'll just, we're going to give up all this parametric modeling and it's all going to be normalizing flows and we're all just going to fit variational approximations to things. I really don't know. I'm reluctant to speculate on what the future looks like. What I do know is the future has a long tail, right? No matter what the future looks like, there's going to be a long tail of people using things like Stan, PyMC, things like that, because it's just people learn things and it takes the generational changes in academia are slow. I remember being like an eager grad student thinking, this whole field's going to be revolutionized in 5 years, and being like, what? People are still doing what they were doing 5 years ago? It's just, it goes with people, not with, everyone doesn't change at once. So I don't know. I think there's going to be a lot more machine learning, a lot more things like normalizing flows and diffusion processes and things. More non-parametric stats than we're doing now.
So more Gaussian processes, you think?
Yeah, Gaussian processes are very expensive, but so there's a lot of work going on here. So like I'm at Flatiron Institute now with a bunch of really great applied math people. And there's work going on here like really accelerating GPs. The way applied math people work is sort of like the way INLA works, if you know that system, right? It's a great nested Laplace system, but they work on, INLA, if you don't know INLA, I would suggest looking it up and maybe inviting some of their devs, because it's a really cool system.
Oh, INLA, you said. Yeah. Yeah, I definitely want to invite some people from INLA. Yeah. If you can make some introduction for me, I'd be very happy.
Sure.
Yeah.
It's a really cool system, but the way they work is very much in applied math mode, where they do very careful analysis of one model or one limited family of model, and then develop a method that works for that. So we've got people here who are building Fourier-embedded Gaussian processes that can scale to like hundreds of millions of data points with exact solutions in 1 or 2 dimensions. But they can't really give you like variance estimates at the same time. They're like that they can do the mean for. So there's a lot of like applied math stuff that's like can make some of these particular instances really fast. But I don't know how much the future is going to look like that, right? And how much the future is going to be black box, where we just sort of write down models and the computation keeps up. Like I think the state of the art is always going to be some mix of automation and custom building.
Yeah. So still some humans in the loop. Yeah. Definitely about INLA. It's an episode that I've been wanting to make for a long time. Also, I have some patrons who asked for it. But to be totally honest, like it always fell apart because of scheduling issues. So as of now, I haven't been able to get some member of the INLA team to come on the show, and I definitely want to. So yeah, like
okay.
If you or anybody listening can make some introduction, I'll be happy to get them.
I know a few of them. I'll send you an introduction. So yeah.
Awesome. Yeah. Thanks a lot. And
it's a small world. Everyone's always asking me if we're competing with PyMC and all these things. And I'm like, no, we're all on the same side. We're all like, we want to just get more people using these kinds of systems. It'll be good for all of us.
Yeah, I mean, exactly. And that's actually something I'm curious about from your experience. How do you answer people's questions about, but why would I use a Bayesian model here? Like, I don't know, I already have an AB model or a regression model that works. Why would I use a Bayesian model here, especially if it's going to be harder to fit?
Yeah, I mean, I don't think there is a good answer to that. I think for a lot of situations, a non-Bayesian model's fine for what you're doing. So I'm generally not in the business of trying to convert people into Bayesians. There's enough people who've converted themselves. I can just work with them. But I think that the motivation for Bayes is, I think, the one we all understand, which is the sort of natural interpretation of probabilities. Right, that everything's just going through probability theory, right? We haven't tied one of our hands behind our back by saying parameters can't be random. So it's the practical systems like PyMC or Stan or something are giving you a way to fit models together compositionally. Right. And I think that compositional aspect of the models, that I can build a COVID model and I can pull out an AR2 prior and couple that with like an ICAR spatial model and then build a GLM for Poisson type data. And it's just really easy to put all those pieces together. Right. If you're in a frequentist world trying to calibrate confidence intervals or something for that, it's a huge amount of math every time you change your models. Right. Whereas the Bayes world is just sort of plug and play and go. Right. Now, you can do that in the frequentist side with something like a bootstrap if all you need is confidence intervals or something, but they tend to be not so stable, which is why everyone's not, right? It's not just the whole frequentist world isn't all doing black box bootstrap. At least that's what they tell me. I've never really tried it myself. But I think the black box nature of Bayes, just being able to write down the model you want, being able to write the data generating process. And it's sort of, I find there's two different ways people look at statistics, often in engineering, and what I think characterized by like the data geometry people. What you'll see is people trying to figure out how they can take their data and somehow transform their data so that it matches a standard model. Whereas I think the sort of standard Bayesian way to do it's the other way around, where you try to code the generative process. And like mainly when I'm trying to teach people how to code models, I'm trying to get them to stop trying to control things themselves and just write down how they think the data came about. And it's hard because people don't believe you can just invert that process. It seems like magic. Like the first time I saw like a mixture model fit, I'm like, how in the world did it do this? I'm like looking at the data. I'm like, there's no way, and it just teases these things apart that don't seem like humans could do it, but we can't. That's why we build computers, I guess.
Yeah. I mean, I agree with that. And that's also what I love in the Bayesian framework is that customizable building block idea. It's like often in the labs team we talk about like Bayesian modeling being more like Legos, when the traditional machine learning models would be more like playmobiles, so way less customizable, even though they are very fun to play with, but you can only play with them in the intended way.
Yeah, they're like the new Lego, where you build a starship with your Lego, and that's all you build. And then you get another box of Lego and build another Star Wars product, or Harry Potter or something.
Yeah. And so that aspect in the black box model, definitely in the interpretation that it gives you from the model is just priceless, for sure.
Yeah, and I think the other big thing is that it's nice to be able to propagate your uncertainty, right? It's just Bayes makes it very natural to propagate your estimation uncertainty and your sampling uncertainty through inference, right? And that's not a problem. It's not something you see done outside the Bayesian world very much.
Yeah, true. And something I love also is that it makes counterfactual analysis way easier, right? Because it's just forward sampling. It's baked into the model already that you can change the data and see what that would mean for the inference side. And I mean, we call that forward sampling, but basically it's related to like counterfactual analysis. And that part for me is really amazing to see, especially when you see people understanding that, wait, that means I can do counterfactual analysis by just swapping the data. Is that right? It's priceless to see the smile on the face.
Yeah, it's very, it's a big jump in statistics. And I find that's one of the harder things to teach people is that retrospectively, we take our observed data like the Ys in regression, and we treat them all counterfactually as if they could have come out differently. Right? So even though we've observed something, we treat it probabilistically. Right. And that's the key. Like what Andrew says is this greases the wheel of commerce. Right. You apply some uncertainty and it lets your inference get unstuck. Like if you were trying to solve all this stuff exactly, you wouldn't get a solution. But you allow some slippage from some uncertainty, and then all of a sudden everything can chunk along.
Yeah, exactly. Yeah, I love that metaphor. Okay, like time is running, and I want to ask you just like two last questions before the last two questions. Like talking about that and discovering Bayes and that basically also philosophy and practicality of the framework, are there any mistakes that you think are good to make when you start learning Bayesian statistics?
No, I'm not even sure what you're thinking about there. Like a mistake that's good to make? Not that I can think of.
Yeah. So, like, for instance, for me, I know that it took me a long time to understand the difference between posterior samples and posterior predictive samples, related to what we just talked about. That posterior predictive samples actually samples that integrate the whole uncertainty of your model, and that would be the observed data, the Ys, as you were saying. And if you imagine that the Ys have a normal likelihood, so Y would be following a normal likelihood with mu and sigma for standard deviation, and the Ys would, of course, be more dispersed than the mu's, and the mu's are usually your posterior samples. I mean, sigma is stupid. And to me, it took me a long time to understand that difference between, okay, the mu's and then the Ys. And I think I made several mistakes about that, like trying to understand that. And after some point, I was like, oh, okay, I get it now. And also trying to come up with my own posterior predictive samples instead of using pm.sample posterior predictive. I would code that up afterwards with NumPy based on the posterior samples that I got to see how you get to those posterior predictive samples. So does that make the question a bit clearer?
Yeah, I wouldn't say that's a good mistake to make, though. I wouldn't encourage people to make that mistake. It's something you need to tease apart, for sure. It's a problem a lot of people have going that. I think the other problem is understanding the difference between standard error and standard deviation in the posterior, right? The idea that a larger sample size will bring your standard error down for estimating the mean, but there's still residual uncertainty because the mean is the mean and you've got standard deviation. So it's like we're always trying to convince people to use fewer posterior draws, right? Because once you've got 100 posterior draws, your posterior mean's identified to within 10% of the posterior standard deviation. So you've eliminated most of the uncertainty at that point, right? And sort of people letting go with that is, I think, really hard, right? Realizing that that's enough, that we've still got residual uncertainty, right? Even if I know this parameter exactly, even if I know the mu exactly, there's still residual uncertainty in the sampling the Ys. So we have to deal with two kinds of posterior uncertainty, our estimation uncertainty in the parameters and our sampling uncertainty in whatever the underlying model is.
Yeah, it's definitely super important indeed. Okay, good. Like I could continue, but maybe can you tell us quickly, what's the next thing you have in mind that you want to learn, that you're curious about?
Oh, that I want to learn? Well, we just had a really cool workshop here on diffusion processes and like normalizing flows and measure transport. So I think the main thing I've been getting into now is normalizing flows and trying to understand variational measures like Wasserstein distance and thinking about variational inference as a kind of Wasserstein distance minimization, kind of like quasi Monte Carlo. So I want to understand much more of those geometry ideas. I'm also trying to learn more Riemannian geometry too, because we're trying to build better samplers that take into account some curvature information.
And so how do you go about that, by the way? Like, are you more of a book reader? Do you listen to podcasts? Do you talk to people?
I'm very much a book and case study reader, and I like to implement stuff to understand it. I generally try to understand things myself, then write it down in math notation I can understand, and then code it. At that point, I usually have to go talk to experts because usually I get stuck coding it. So like with normalizing flows, I could understand all the math in the tutorials, but all the tutorials were like, oh, just plug a convex function in here. Oh, just plug any kind of thing. And I'm like, can you just give me one example? Like I want one normalizing flow I can code that I don't have to make like 5 arbitrary decisions on, because I'm not quite sure the space you're trying to ask me to make decisions in. They're like, you need a link function. Well, maybe you're going to use ReLU. Maybe you're going to use a leaky ReLU. Maybe you're going to use soft plus. You're going to use something there, right? And all the tutorials are all just, and the stats literature is the same way. It's written for people who understand it already, right? So they leave a lot of decision points open, and it's very hard to code. And for me, I don't understand stuff till I can actually get it coded. Like actually like have an algorithm. Like I'm a computer scientist, so I like to, writing the math down's good, but I don't like papers where the algorithms are written where they say C formula 3 and C formula 5, and you realize, formula 3 is not enough for me to fill in this blank in this pseudocode. So I'm usually arguing with my co-authors to write more explicit pseudocode. Although our last paper to JMLR, they pushed back and said, this is like too much. It's like everybody knows this. And I'm trying to say, no, everybody doesn't know this. We learned this, like Lu Zhang, the person I was working on this paper with, she went and read 1970s Fortran code to learn this. There were no papers that had, there's no textbooks. It was like, we're trying to do a service here. And people are like, nah, that's like too pedantic. Let's give us something sketchy that no one will be able to replicate.
Yeah.
We compromised and pushed it all off to the appendix.
Yeah. Well, Bob, thanks a lot for taking the time. I've still a zillion questions for you, but let's call it a show. Before that, of course, I'm going to ask you the 2 final questions I ask every guest. So first one, if you had unlimited time and resources, which problem would you try to solve?
I would go back to natural language semantics. That was my original love. And I would, the problem I want to solve is metaphor. How we do associative reasoning as humans. How do our words have meanings? How do we understand each other? How does our language connect to the world? And how does this all, having all this stuff floating around in our head, let us talk to each other? Sort of the deep natural language questions, linguistics questions, I still find most interesting. There's not like technical questions in Bayes stats I want to figure out. To me, that's a much more practical thing. I'm not good enough at the theory to really think that I will ever make progress in Bayesian theory. Right? When I was doing linguistics, I told people I wanted to work on metaphor, and Barbara Partee, who was a very senior person in my field, told me, she said, I'll tell you what, when you get tenure, you can work on it on your sabbatical years. That's a good amount of time to work on a problem that hard. And I'm like, that's a real bummer. So you learn that when you come to academia, as everybody works on very narrow problems. You want to solve metaphor? Yeah, you're gonna work on one preposition. That's what you're gonna work on. You're gonna work on metaphor for the word on for 20 years.
Well, actually, related to that, I'm reading a book right now by Robert Burton called On Being Certain, Believing You Are Right, Even When You're Not. He's a neuroscientist, and that's a bit related to what you said, and NLP and stuff like that. And the book is really fascinating. So
yeah, in my mind, it's a cognitive question. It's not a philosophical question. It's really like, how do our brains work? How do our brains let us do this kind of associative reasoning we do?
Yeah. And it's like, so the book, it talks a lot about that, and that's really fascinating. I love it and definitely recommend it. And I put it in the show notes. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I think I'd go back to my first problem. I think I'd probably choose Wittgenstein. Or maybe Quine, one of the early 20th century philosophers of language who kind of threw out so there was a huge movement in the 20th century of logical positivism and trying to be a very reductionist notion of language. And Wittgenstein and then Quine finally put the nail in that coffin of, that language is really constructed by human agents. It's really associative. It's about human agents. It's not about discovering meaning in the world. So I think Quine or Wittgenstein would be or maybe Richard Rorty. It's sort of going up in time. He's the most recent. He's no longer alive, but incredible philosopher, sort of changed philosophy of language dramatically in the later 20th century in a way that I think was good.
Okay, well, I have nothing to argue here. That sounds like a absolutely fascinating dinner. So just make sure to invite me, please.
Yeah, Okay. Yeah, I'm usually happy eating dinner with anybody. I like eating dinner with our postdoc candidates. So, I'm easy.
Okay. Well, thanks a lot, Bob. I really learned a lot, and that was really cool to talk to you about that mix of math, history, of stats. That was super cool. I learned a lot of things. And as usual, I'll put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Bob, for taking the time and being on this show.
Thanks a lot, Alex.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.